The following presentation is a documentation of a full-depth reclamation construction project using cement slurry and microcracking. Redwood Drive is located in Salt Lake City, near California Avenue and Redwood Road. And on this map, Redwood Drive is highlighted in red. The local climate for Redwood Drive is widely variable. The winters are cold and the temperatures often stay below 32 degrees Fahrenheit. The summers are hot and dry and the temperatures often reach 100 degrees Fahrenheit. This was the case during this construction project. The transition periods are relatively wet, and roads are often affected by spring freezing and thawing. Redwood Drive, prior to reconstruction, suffered from severe pavement failure due to fatigue cracking and insufficient drainage that resulted in ponding. The average International Roughness Index reading prior to reconstruction was 155 inches per mile, which is characterized as fair according to the Federal Highway Administration. The pavement structure consisted of 3 inches of asphalt, 5 inches of road base, and a clay subgrade. California bearing ratio values for the subgrade were generally between 5 and 10. The reconstruction design for Redwood Drive consisted of a full-depth reclamation process with cement stabilization and a cement content of 4% to achieve a 7-day unconfined compressive strength of 400 psi. Which is consistent with current recommendations for the design of cement-treated bases in frost-affected areas. The reclaimed cement-treated base was designed to be 8 inches thick, with a 4-inch asphalt overlay. The classification of the blended base material was A1B, according to the American Association of State Highway and Transportation Officials, and a poorly graded sand with gravel, according to the Unified Soil Classification System. Normally, cement stabilization is done by spreading cement powder, which can produce unacceptable air quality conditions due to fugitive dust. Because Redwood Drive is a residential area, the safety of the residents' health was of primary concern. In order to reduce the health hazard involved with cement dust, the cement was spread as a cement slurry with a set retarder delaying the set time by about 2 hours. The purpose of the remainder of this video is to document the construction of the new pavement structure. The construction process consisted of several steps. In conjunction with Step 6, the BYU research team gathered cement samples and prepared manual compaction specimens of field mixed cement treated base. 1. Pulverization of asphalt surface. 2. Excavation of pulverized asphalt and base material. 3. Over-excavation of subgrade. 4. Replacement of wrap-based blend. Salt Lake City Corporation managed the construction project. Newman Construction was the general contractor on the project. Jack B. Parson Companies was the subcontractor providing and distributing the cement slurry. The Brigham Young University Materials and Pavements Research Team worked with Salt Lake City Corporation and Newman Construction to document and gather data relevant to the construction process. As mentioned previously, the subgrade was essentially clay. Due to elevation constraints, the reconstruction included having to remove some of the existing subgrade. This was a very expensive and time-consuming process, but was successfully accomplished. As part of the excavation of the subgrade, the wrap-based blend was moved to the opposite lane as shown in this video. The subgrade was graded and the excess was hauled off-site. The wrap-based blend was then replaced for final grading before the cement slurry was applied. 5. Initial grading and scarification of wrap-based blend. 6. Application and mixing of cement slurry. The cement slurry, having an average water-cement ratio of 0.44, was spread directly onto the scarified wrap-based blend. The slurry was then spread across the scarified base manually. Scarification of the base layer was done to loosen up the compacted base layer. However, the cement slurry was more easily spread on an unscarified base. The cement slurry was mixed into the base course using a pulverizer. The pulverizer made one pass down the road, and an 8-ton vibratory roller passed behind the pulverizer to compact the freshly mixed CTB. On the day of CTB reconstruction, the air temperature reached 102 degrees Fahrenheit, the wind speed was insignificant, and the relative humidity was around 10%. Previous BYU research indicates that in those conditions, use of a set retarder, as applied on this project, is warranted. 7. Compaction and curing. This project was the first known project where cement slurry and microcracking of the cement-treated base layer were implemented in the state of Utah. Subsequent to pulverizing, 2 plastic bags were filled with freshly mixed CTB material from each of 10 sampling sites. The mixed CTB material was then immediately used to make specimens 4 inches in diameter and approximately 4.5 inches in height. These were compacted with manually operated modified proctor hammers. BYU researchers prepared 4 specimens per site, resulting in 40 specimens total. Each specimen was extruded from the compaction mold using a hydraulic extruder. Following extrusion from the mold, each specimen was inserted and sealed in a plastic bag, clearly marked for documentation, and placed in a large cooler for temperature control and easy transport. These specimens were prepared for unconfined compressive strength testing at specific curing times at the BYU Highway and Materials Laboratory. The average 7-day strength was 417 psi. Proper care needs to be taken when curing CTB. Cement requires proper moist curing to ensure that enough water is provided for cement hydration. The moist curing process was ensured by spraying the CTB with water using a water truck. 8. Microcracking. Microcracking was performed 2 days after the final compaction of the CTB. An 8-ton vibratory roller was used to microcrack the new CTB. 48 hours after final compaction of the CTB was sufficient time for the CTB to gain significant strength, especially during the hot summer month of August experienced in 2008. The target reduction in strength of the CTB was 40%, using the portable falling weight deflectometer. Between 2 and 4 vibratory roller passes were required to achieve the target reduction in CTB strength. Measurements were made between each individual pass. For clarification, 1 pass is down, as opposed to down and back. Once the target reduction was reached, the contractor was notified to discontinue vibratory rolling. The purpose of microcracking is to reduce the development of large shrinkage cracks in cement-treated base by creating a network of fine cracks less likely to propagate into an asphalt surface course. Aside from taking measurements of the base stiffness using instruments, inspectors may evaluate microcracking visually. The process of microcracking should not significantly change the texture of the surface. In fact, cracks should be defined enough to be barely noticeable. If microcracking is properly performed, the CTB will regain its strength within 2 or 3 days. 9. Paving of surface layer. And finally, the wearing surface, a 4-inch dense graded asphalt, was placed on the CTB. In summary, the reconstruction of Redwood Drive involved full-depth reclamation using cement slurry and microcracking. This method was selected for use in this urban residential area to completely eliminate the problem of fugitive dust associated with the typical method of cement application. The reconstructed pavement should provide excellent serviceability for this neighborhood for years to come. This video was produced by Charles Hope and Spencer Guthrie.